So, hello everyone. So, I welcome you to this live interaction session for the course Introduction to Abstract Group Theory. Let me just share my screen. I hope it's visible. Okay, so
Yes, sir.
we are going to solve assignment 4 today. The first problem is let G be a group of order 189 and H be a normal subgroup of G of order 9. By G by H, we denote the quotient group of this normal subgroup inside G, and then we need to choose all correct statements. First statement is the order of G by H is 21. Second is the quotient G by H contains an element of order 4. And the third one is the number of left cossets of H is H in G is 21. And fourth is about the number of right cossets of H in G, which as per the option is less than 12. So we can start by with the first part. So is it true that the order of G by H is 21?
Yes, sir. It's just 189 by 9. So,
Can you say it a bit louder?
um, so the first statement is true.
First is true, and the reason is
Um, well, order of G mod H is um, order of G by order of H, which is 189 by 9, which is 21.
very good. So order of uh, G mod H is just the order of uh, G by order of H, and that is 189 by 9. So it's 21. The first part is correct. What about the second one?
Second
Does
one's not true. 4 doesn't divide 21.
good. So as an application of the Lagrange theorem, we know that the order of an element divides the order of an order of the group. So since 4 does not divide 21, therefore uh, there exists does not exist an element of order 4 in G by H. Good. What about the third one? The number of left cossets of H in G is 21.
That's true. So,
That is true because the order of G by H is same as the number of left cossets of H in G, and since all left cossets are also right cossets, because the group is normal, subgroup is normal, so this is also the number of right cossets of H in G, and that is 21. So this is not just third, but we are also solving the fourth part. Okay, so this is correct, but not correct. Okay, so it is clear. We can move to the next part. Let me just paste the question here. Like denotes the parity group of integers, and G by and Z by 36 Z is our G. And the subgroup H is 3Z modulo 36Z. Then clearly this is a subgroup of G because here we are taking quotient of the entire Z by 36Z, and here we are taking the quotient of 3Z by 36Z. So this subgroup sits inside G. Now we need to choose the statements. First is the order of first and second is related to the order of H. So what you say? What should be the order of H?
Well,
Y1. So here we can't use that order of H is order of G by order of order of H is just order of 3Z by 36Z because both are infinite. So that won't give you anything. So how to show that order of H is uh, 3 or 12? First of all,
one, so I could first consider Z mod 3Z and Z mod 36Z.
you can first.
Oh, no, sorry, I'm wrong.
Hmm. So we need to first understand what kind of elements are there in H, right? So as per the definition, H is 3Z by uh, 36Z. So, see, what if we write? So, can you tell me what kind of elements are there in Z mod 3Z?
Mod 1, mod 0, mod 1, and mod 2. So,
Mod 2. So, here the kind of elements are uh, 3Z plus A, where A is varying from 0, 1, and 2, right? And 0, 1, and 2 are modulo classes when we divide an integer by 3. So, with the same split, we can say that here the element would be this is nothing but a collection of all elements A plus 36 Z such that A or A belongs to the modulo class of 36. But now we need to choose uh, elements uh, from 3Z, not from Z. So they should be of the form uh, 0 is okay, 3, 6, 9, 12, 18, 21, 24. So they should be multiple of 36. Oh, sorry, multiple of 3. 27, 30, 33. And 36 is 0. So uh, this is what does this set contains? This set contains modulo classes of 36, where the remainder is a multiple of 3. You got it? If we just focusing on Z modulo 36Z, then you would be considering this A from 0 to 35. But here, we're just taking the quotients in such a way that A is varying over 3Z. Clear?
yes, sir.
Good. Now, if two, none of them will be so. what I mean to say, if say A plus 36Z is same as B plus 36Z, where A and B are belonging to this set, then can we have a contradiction? A not equal to B, of course. Can we have a contradiction? So see, what does this imply? This will imply A minus B will be inside 36Z. And that means A minus B is divisible by 36Z. It's divisible by 36, which is a contradiction since A is not equal to B and A, B both are less than 36, right? So by this, what we conclude that this set has all the has distinct element and thus the cardinality of H is 12. Okay, is it fine?
Yes, sir.
This implies size of H is 12. And this is true in general. So let this is an exercise for you. Exercise so that actually write if n div uh, n divides let me write it in full. N divides m, then show that size of nz by I should not write like that. Size of nz by mz is m by n. Okay. So 3 and 36 are not special cases. With this you can extend to anything such that this n divides 36. 36 divided by 3 is 12. The same proof will work. Okay. So this option is correct and this is not correct. Now the next part is the quotient group Z modulo H has order
Sir,
12. Yes.
so I could also consider Z mod 3Z and Z mod 36Z and then take the quotient of them both, right? Then also I would get the same.
But then you need to show that Z mod 36 Z modulo Z mod 3Z is isomorphic to H.
Oh,
So, you're getting my point? So this group need to show that this is isomorphic to what you are saying. Z mod 36Z divided by modulo by Z mod 3Z. This no, doesn't comes directly, right?
yes.
You need to show that.
Okay.
Or maybe not. So you know this third theorem of isomorphism.
Sorry, sir.
The third theorem of isomorphism is somehow like this only?
Um, yes, sir,
Just check.
um, but
I don't
then
know. They are assuming finite groups or not. The third theorem of isomorphism is like that only, that V mod H modulo G mod K is isomorphic to H modulo K if K is a normal subgroup of H. Something like that is there. So you can just check. But somehow you need to come up with this proof that this group is isomorphic to this group. If that theorem helps you, then it's good. Otherwise, you need to prove it of your own. Okay?
don't
Then only
think
you can.
the third theorem helps. So um, so it only tells that if H and K are normal subgroups of G,
Uh,
then G mod H mod um, K mod H will be isomorphic to G mod K, where K is
will
also
okay.
H is a normal subgroup of K.
Okay. So
H
then
is
this will not work.
yes. Sir.
Hmm, right. But this uh, should be true, I guess. You just check. Okay. Okay. So now it says the quotient group G by H has order 12. So you have this G, you have H. The second and the fourth part is G mod H is isomorphic to Z mod 3Z. Here maybe the third theorem can help us or no. Although we don't require that. So what we can say about G by H when G is this and H is this.
So this is not true.
This is not true. What about the next one?
That's true. That's just the third theorem of isomorphism.
The theorem of isomorphism. So, I'm giving you two methods to come up with this. Method one is, so here G and H both are finite, right? So we can use this order criteria. The order of G by H is mod G by mod H. And what is mod G? This is Z mod 36Z, right? So this is 30, it has order 36, it has order 12. This is 36 by 12, hence it is just 3. And we know that there is a unique uh, group of order 3 up to isomorphism. So G by H is isomorphic to morphic to Z mod 3Z. Okay. Second is what you said. By the third theorem of isomorphism. Uh, G by H, that is Z modulo 36 Z divided by, not, it's not divide, it's how to write this. Z modulo 36 Z modulo Z modulo 3Z modulo 36Z is isomorphic to Z mod 3Z. Okay. So this method will fail when there won't be a unique group of that order. But this is a general method, so it will work. For example, uh, if instead of 3Z we are having 4Z, then uh, Z mod 36Z modulo 4Z by 36Z will give us Z modulo 4Z. But this will tell us that 36 by 4Z modulo 36Z will become here 9. So it will just tell us that order of G by H is 4. But that won't imply that G by H is isomorphic to uh, Z mod 4Z. Okay. But there also you can use some other trick if you want to apply this order criteria. What? So this group is uh, cyclic, right? So whatever quotient you have, that is also going to be cyclic, right? So once you have the order, then you can directly say that its factor group is cyclic, hence it has to be of order 4. So it will come up as Z modulo 4Z. So that will work even if the order is not 3. Okay. Uh, is it clear what I just said?
Not.
I'm saying, uh, I just said that this method is true in any situation, whether here you have 3, 4, or 5, any number. But uh, once you have some other integer which is not prime, then uh, you cannot directly say that the z g by h is isomorphic to z modulo nz if instead of 3 you have some n which is not prime. But you know that this group z modulo 36z or anything else from which you are taking the quotient, if this group is cyclic, the factor group has to be cyclic. So this group has to be isomorphic to the cyclic group, and thus, in, even if the number is not a prime, in similar kind of situation, you will always get Z modulo and Z by method 1 also. So without using the third theorem of isomorphism, also you can conclude in the similar manner. Okay.
Okay, sir.
Okay. Let me just. This finishes second question, right? This part is not correct, but this is correct. Let me just move to the next part. So we need to choose the correct statements. Mm, yeah. So the first part is S3 has a quotient group of order 3. Is it correct?
No, sir.
Why?
Um, so, so considering any order 2 subgroup, there's no normal subgroup of order 2. So, S3 can't have a quotient group of order 3. So
Okay.
6
So,
by uh, 6 by 2 has to give 3, but there's no normal subgroup of order 2.
Very good. So since order of S3 is 6, uh, if S3 has a quotient group of order 3, then there should exist H, a normal subgroup in G with order of H to be 6 by 3, that is 2. But the order 2 subgroups of S3 are not normal in S3. What are order 2 subgroups? Just the element generated by order 2, which is identity 1, 1, 2 and identity 1, 3, and the third one is identity and 2, 3. And we have checked it earlier that they are not closed under the conjugation. So they are not normal subgroups of S3. Okay, the first one is not correct. What about the second one? Let G be a group. Suppose that there exists a non-trivial homomorphism from Z to G, and by non-trivial homomorphism we mean uh, the kernel of the homomorphism is not the entire domain, or in other words, not everything in the domain is mapping to the identity. There exists at least one element in the domain which is mapping to a non-identity element. So here the option says that for a group G, if there is a non-trivial homomorphism from Z to G, then G is finite. So is it true?
No, sir.
No. Why?
So, since this is non-trivial and um, Z is cyclic,
Hmm.
so one has to map to some non-zero element. And the suppose one maps to some A belonging to G,
Hmm.
then A has some finite order, which would mean um, so which would mean that phi of one also should map back to the identity element, but this has but the this is an infinite cycle, so it can't happen.
Ah, not very much convinced. So you only have uh, we have just order of A. We have some relation between order of A and order of phi A. Or it is just says that order of phi A should divide order of A, right? But that doesn't conclude that order of IA cannot be infinite. For example, you can take G to be just Z mod 2Z, which is just Z2, which we denote, right? We can map all even integers to 0 and all odd integers to 1. That's a homomorphism, non-trivial homomorphism. G can be finite, but is it always finite? That's the question. We cannot say that it. So the option is not saying that it will never be finite. It's saying that it will always be finite. So if we want to disprove it, we just need to give a counter example.
Sir?
We we are not supposed to show that in all the situations G is infinite. And actually, that's not the case. This is an example.
Mm.
If uh,
So suppose phi of 1 maps to some A, phi of 1 equals A,
uh,
and suppose A power n equals E for
P of
some
A
n
is
belonging
1.
to n.
Can you just repeat? P of 1 is 1.
Phi of 1 is A, where A
Okay,
belongs to G.
right,
And suppose A power n equals E, where n is order of A.
uh,
Um, so that means phi of 1 power n equals E,
right,
which means phi of 1 power n is E.
right, which
But
just
then,
means that P of N is mapping to E. So that's not a problem.
oh, okay, sir. Yeah.
It doesn't imply that N is identity. It just says that N is mapping to identity, which is fine. As I gave you the example, na? Map all odd integers to 1 and map all even integers to 0. So that's what the homomorphism from Z to uh, Z mod 2Z. You just map every odd integer to 1 plus 2Z and even integers to uh, 0 plus 2Z. So that's the homomorphism. But Z mod 2Z just has order 2.
Got it, sir.
Here you can say your uh, P of 1 will map to is just 1 plus 2Z. And 1 square is, so here phi of 1 is 1 plus 2Z. And 1 plus 2Z square is 1. So phi of 1 square is 0 plus 2Z. This just means that 1 square is 0 plus 2Z and 2 mapping to 0 plus 2Z. That's fine. 2 is an even integer, so that's what we are supposed to get. It has to map to 0 plus 2Z. So this says that not in every case we will get G is infinite. There are cases when G can be finite. But is it the situation every time? To disprove it, we just need to give a counter example.
Oh, so I can just have the identity map from Z to Z, right? That would be non-trivial. And Z is infinite.
Right. So that will work. So you can just map, you can take G to the Z and uh, then this will work. And can we have more such maps? You can take any non-trivial subgroup of Z. So take G to be any NZ where N is non-zero. Define the map phi from Z to G as A mapping to NA. Then this is clearly a homomorphism, right? You can check that. A plus B will map to NA plus NB, which is N of A plus B, and that's what the image of A plus B, right? So this implies phi is a homomorphism. and hence, uh, but G is infinite. So the example that you gave is just when n is 1. Okay, but you can take any non-trivial subgroup of G, non-trivial subgroup of Z, and the same example works. Clear?
Yes, sir.
Okay, good. So this option is also not correct. What about the third one? A G be a group, and suppose that there is a non-trivial homomorphism. Now from G to Z, then can we say that G is infinite? Now, in this case, again, if it is not true, you just need to produce a finite group G such that you get a non-trivial homomorphism from G to Z. But if you want to show that this is true, then you have to actually prove it. So, what do you uh, expect, that is it true or false?
Yeah, this is true. I think now my argument will work. So,
Hmm.
suppose some A belongs to G.
Uh,
Okay. So, again, since Z is cyclic and the homomorphism is non-trivial, there
hmm.
exists some A belonging to G such that phi of A equals 1.
No,
Mm.
it doesn't say that the homomorphism is subjective.
Um, but
If
since
P
1
of
is
1 is mapping to 1, then the homomorphism has to be surjective, because then uh, the element n will have the pre-image as phi of a raised to n. But so we can have even non-surjective, non-trivial homomorphisms.
um, sir, if oh,
For example, you just consider G to be 3Z,
oh, e- e-
and the inclusion map from G to Z, then one will not have any pre-image.
oh, yeah. Okay, so suppose
Hmm.
phi of uh, phi of A equals some non-trivial element in Z.
Right?
Suppose phi of A equals n.
Okay.
Now, and suppose that G is finite,
Hmm.
then A has some finite order.
Right.
So, suppose A has order m,
Hmm.
phi of A power m equals phi of A power m, which is the identity, but this implies that n power m um,
Right.
is 0, which can't happen.
Which can't happen because n is non-trivial. Good. So, uh, again, I will give you two methods. First is, let's first start with what uh, Prerna says. Uh, so let uh, so since they are giving some notation or not? No. So let me just first say that let phi from G to Z be a non-trivial homomorphism. Non-trivial homomorphism. Then there exists some A which is not equal to 0 belongs to image of phi, right? Let G belongs to G be such that uh, phi of G is A, right? Uh, if order of G is less than infinity, means if G is finite, then order of G has to be finite, and that will implies uh, there exists some M belongs to N such that order of G is equal to M, which implies G raised to M is equal to identity of G, right? And then this will implies phi of Gm is phi of identity of G, and which is 0. But phi of Gm is phi G raised to M, which is A raised to M, and in integers, this is just M times A, and that will implies order of A is M, which is less than infinity. This is less than infinity. This is contradiction 2. A is, and I can simply say, so we know that in integers only 0 have finite order. This is contradiction to A not equal to 0. Okay. Now, here is one observation. First of all, this will implies order of G is infinite. Okay. So now, observation is the above proof also implies that there exists an element of infinite order in G. Not just we conclude that G is infinite, but the same process we can also conclude that there exists an element of infinite order in G. So it's we are getting even more if we follow this same process, because see, all elements are of finite order, then order of G is finite and the same thing will work, right? So no need to assume that order of G is finite. Even if we just assume that all elements of G have finite order, then also the same proof will work. Okay. So assuming that the order of G is finite uh, is even a weaker condition. We can get even stronger conclusion, and that is there exists an element of infinite order in G, right? So this also discards the possibilities of groups which are infinite, but which has each element of finite order. For example, uh, the group Q modulo Z. This is an infinite group, but each element of Q modulo Z has finite order. So this observation also discards uh, possibilities of having such a group. Okay. Although the option does not discards this. Option just says that the group should be infinite. Okay. Okay. Now, simpler method, but we won't get this observation through that. So it says, uh, so this means if there is a non-trivial homomorphism, that means that there will be some kernel, right? So let phi from G to Z be a non-trivial homomorphism, then two things we can conclude. Kernel of phi is not the entire G, and image of phi is not the singleton set 0, right? Because the kernel homomorphism is non-trivial, so not everything is mapping to 0. Okay. Now, since or, or we also know that uh, G mod kernel phi is always isomorphic to image of phi, right? This is also true. And since image of phi is non-trivial, and we also know that in every case, this image is a subgroup of Z, right? So it's a non-trivial subgroup of Z. Image of phi is also a subgroup of Z, right? So what does this means? This means there exists n not equal to 0 belongs to n such that image of phi is equal to some nz. Clear? Because these are the only non-trivial subgroups of Z. And this will implies that G mod kernel phi is isomorphic to nz, right? Now this is infinite. This is infinite. So this implies Z mod kernel phi is infinite. And clearly, if a factor group of a group is infinite, this will implies G is also infinite. But from here, directly we can't conclude that all elements of G cannot be of finite order. So although both of the methods are correct, to come to a conclusion, uh, as far as the option is this, but this method is also giving us something extra, that is that all elements of G cannot be of finite order. There exists some element of G which is of infinite order. Okay. Is there any doubt in this option?
No, sir.
Okay. So what about the last one? S3 has a quotient group of order 2.
This is true.
This is true. Why?
Um, so S3 has uh, only three normal subgroups, and so it's the identity and S3 itself, and the other one contains the three three cycles and the identity. So uh, the it so if the order of G mod H has to be 2, then order of H should be 3, and we know
Hmm.
that there exists such normal subgroup, so this is true.
Okay. So uh, the subgroup H containing the identity cycle 1, 2, 3, 1, 3, 2, is a normal subgroup of S3? And is it anything special about this subgroup? So this subgroup is basically the subgroup of all even permutations. And we have already seen that the subgroup of all even permutations is a normal subgroup in Sn. So not just for uh, An, sorry, not just for S3, for any n. Sn, the subgroup of all even permutations is normal, and this has order, just order of Sn by 2, and hence uh, the factor group will has order 2. So S3 is not a special case. Every subgroup, every group Sn, every symmetric group Sn has a quotient group of order 2. So in this case, we are just saying that we take this H to be the one which contains all even permutations, which is precisely the subgroup generated by the cycle 1, 2, 3, is a normal subgroup in S3, and order of S3 modulo H is just order of S3 by order of H, which is 6 by 2 or 6 by 3, and this is 2. So in fact, for any n, the group Sn has the subgroup An containing all even side permutations and order of An is n factorial by 2, which thus order of Sn modulo Sn normal is a normal subgroup An containing all even permutations, and An is just factorial n by 2. Thus Sn by An will have order 2. Okay, so S3 is not a special case. This is true for any symmetric group Sn. Okay, so this is also correct. Shall we move to the next question?
Yes, sir.
Okay. So let's do the fourth part. Choose the options in which G by H is an abelian group. Uh, just a minute. Okay. Sorry for the disturbance. So in, we need to choose the options in which G by H is an abelian group. So in first option we have uh, P to be G, which is the additive group of complex numbers, and H to be the group of integers. So is it true that G by H is an abelian group?
Yes, sir. So if
Why?
if H is abelian, then G mod H is abelian.
If G is abelian, then we can say that G by H is abelian.
Yes.
Okay, so since G is abelian in this case, here I'm just writing it here. Since G is abelian, this will implies G by H is abelian. What about the second part? G is GL2R and H is the subgroup containing identity and minus of identity.
This is not true.
Why?
So consider the suppose A equals 1110 and
Mhm.
B equals 1011.
Okay.
So
They won't commute, right? That is okay, but
yeah,
uh, does it imply that the factor group G by H is non-abelian?
yes, sir. So if I consider uh,
So first of
A,
all, if G by H is abelian, let me just do a bit of writing. So if G by H is abelian, then then uh, A H times BH should be equal to BH times AH for all AB inside G, right? And that implies ABH should be equal to BAH, which implies AB times uh, BA inverse must be inside H, and which means AB, A inverse, B inverse must belongs to H for all AB in G, right? So now you just need to produce two elements A and B such that AB, A inverse, B inverse is not inside H. So can you now tell me your example? A is what?
I took 1110. If we go
So this is
clockwise,
1, 1, 1, 0. B is
um, so
0, 1, 1, 1. That's what you are saying?
so
Or something else?
um okay, this is slightly different, but even this might work.
You can tell yours. We can go with that first.
Oh, for A, I had taken for A, I had just switched the bottom two elements.
So 1, 0, 1, 1.
So 1 1 and so I just switched 0 and 1 for A.
Okay. This one,
Yes, sir.
and B.
And then I took A transpose for B.
So A transpose is 1, 0, 1, 1, right?
Yes, sir.
So what is A inverse? This will be just 1, 1, 0, minus 1, right? And B inverse will be 1, 1, minus 1 and 0. So what will be A, B, A inverse and B inverse? 1, 1, 0, 1 and 1, 0, 1, 1, 1, minus 1, 0, 1, 1, 0, minus 1 and 1. So let us first multiply these two. What will you get? So this will be 2 and 1, 1, 1, right? Please check the calculation if I'm doing anything wrong. Then we can multiply these two. Any doubt, Prerna? Okay, so this will give 2 again, and this will be 1, or sorry, minus 1, and this will be minus 1, 0, 1, right? What it will be? This will be 4 minus 1, 3, minus 2, 1, 1, oh, sorry, minus 1, and then 2 minus 1, this is 1, and this is minus 1 plus 1, 0. So this clearly does not belongs to H. Please check if I have done some mistake in calculation. I hope that should be correct. So thus,
It's correct.
okay, thank you. So here we have AH, BH, not same as BH, AH. Okay. This implies G modulo H is not abelian. Fine. What about the third one? If G is a group of order 24 and H is a subgroup of G of order 12, then
This is true.
why
G mod H has um,
order of G mod H is just order of G by order of H, which is 2, which implies G mod H is isomorphic to Z mod 2Z, which is abelian. So this is also correct. What about G to be S4 and H to be E1, 2?
So here G mod H is not even normal, right?
So H is not even normal. So this is not even a group. G mod H can be defined as just a coset set of cosets of H, but that won't be a group. So this here H is not normal, not normal in G, and this implies H is G mod H is not a group. Okay, so this is not true. Good. So I think we can move to the next part. Let G be a group of order 546. H be a subgroup of G. We need to choose all correct statements. G is always abelian. Is it true?
No, sir. But I haven't
Is
been able to find some concrete counter example.
how?
Um,
Uh, what, what's the doubt?
so I know that statement one is not true, but then I can't find a counter example.
So, what's the non-abelian, smallest non-abelian groups, or what are some non-abelian groups that you know?
Well, S3. So any I could yeah, S3 works.
That's the only non-abelian group you know?
Sir?
That is the only non-abelian group you know?
No, well, I could take the s- I could take all the permutation groups where n is greater than or equal to 3. They would all work.
Okay. And do you know any other uh, groups which are not abelian?
Um, well, if I consider groups of even infinite order, then I can take GLN or
Now,
something.
even for finite order, I have already discussed some examples. Those won't be required in this case, but you should know. For order 8, we have seen uh, groups that we have seen the quaternion group and the dihedral group, right?
Yes, sir.
Dihedral groups are also non-abelian. If you take if you are denoting it, say for with the notation D2n, then if n is greater than equal to 3, then the dihedral groups are always non-abelian.
Yes, sir. So,
So you
sir,
can you can generate
that,
more than one example by whatever you know till now. Hmm.
So the dihedral groups are isomorphic to the permutation group, right?
No, no,
No?
no. Just when the order is 6.
Okay, sir.
For example, your D8, the dihedral group of 8 elements, cannot be isomorphic to a permutation group because permutation group always has the order n factorial, right? But can you write 8 as a factorial of some number?
No, sir.
No. So D8 is a counter example to what you are saying. So in fact, once you so both these are non-abelian groups, Sn and D2n, and they only have this intersection of D6 and S3. This is the common point. And after that, they are far apart because the order of dihedral groups is uh, 2n, which, which is uh, so the order of D2n is the dihedral group is 2n. And can it be equal to some m factorial? Because if it is isomorphic to some Sn, then its order should be m factorial, right?
Yes, sir.
But
Got
m is having this m minus 1, and then this multiplication space, right? What does this mean? This means your n has to be some m times m minus 1, m minus 2, and 3. If your n is of this particular type, then only uh, they have the same order. That's when you focus on the order thing. But there are other properties which uh, will stop uh, you from making this isomorphism.
Yes, sir.
So D2 hand has a will always has an element of order n, but you need to check whether this permutation group has an element of order n, where n is m factorial by 2. So this is what this n is just m factorial by 2, right? So the question is, does Sm has an element of uh, order m factorial by 2? For example, when you take m to be 4, 4 factorial is 24, right? So does S4 has element of order 12? No, it won't. Similarly, can we say that S5 has element of 5 factorial by 2, that is 60? See, what is the order of an element in Sm? You just write everything as a product of disjoint cycles, and the order of then the LCM of orders of those cycles is the order of that element. So if S4 has an element of order n factorial by 4 factorial by 2, that is 12, then there must exist some sigma which has the disjoint cycle composition for which the cycle lengths will give you this the LCM 12. What is the easiest way to get this? That through uh, even the 6 into 4 won't give you. You should have a cycle of length 4 and a cycle of length 3. That's the minimal uh, symbols you need. So there should be some cycle of length 4 and some cycle of length 3. So you need at least 7 elements, 7 indices to be moved. But S4 has just 4. Similarly, for this S5, uh, 5 factorial by 2 is 120 by 2 is 60. So you should get an element of order 60. But for 60, uh, the prime factorization is 2, 3, and 5. So the minimum number of elements, so there should be a 2 cycle, there should be a 3 cycle, and there should be a 5 cycle in the cycle decomposition of some element sigma. Of course, you can say that I can do this with by taking some element of order 6 and element of order 5, but then you need 6 cycle and 5 cycle. Even more symbols are required. Here it is 2 plus 3 plus 5, 10. Here you need 6 plus 5. So this is the minimal uh, thing, minimum number of symbols. So here again you need at least 10 elements. So to get an element, at least 10 symbols to get an element of order 60. So similarly, you will see that in SM, you cannot have an element of order m factorial by 2 except when m is 3. So although I have not verified it of my own, but I believe that they intersect only at order 6. Here you get D6 and here you get S3. Okay, you should check it by your own. But I believe that these are two different non-abelian families of groups which have only one uh, member common, that is S3, and which is same as D6. Okay.
Okay, sir. That's okay.
Okay.
Thank you.
So this is thing extra. Uh, now, can you now produce two non-abelian groups for me?
Mm. Well, now I can just consider D273.
D273. Good. So, solution is D2n is non-abelian. And now you also should check why this is non-abelian. What are the elements which won't commute? Okay. Therefore, for non-abelian for when n is greater than equal to 3. If you take n to be 2, then this will be D4, which will be the Klein group, which is abelian, right? I think D2n is always defined when n is greater than equal to 3 because we we define it as a symmetries of regular n-gon. But anyway, let's just write it. Therefore, D2 times 273, right?
Yes, sir.
Is a non-abelian group of order 546. So for every even order so for every even order greater than 4, there exists a non-abelian group of that order, right?
Sir,
You
can
agree?
you repeat this statement?
Huh. So I want to say that if uh, so for every even order, when the order is greater than equal to 6, the register non-abelian group of that order. You can precisely take D2n, right?
Yes, but uh, I don't understand how this is true in general.
So if n is even, or I should not write n, m is even, and m is greater than equal to 6, then the group D 2 times m by 2 is an is an non-abelian group, right? You
Yes,
get the point,
uh,
right?
in the context of dihedral groups, I agree. I thought you were telling in general for any groups, but yeah, this point I get.
So there is just at least one example. But can you say the same for odd? When n is odd, then can we say that after certain uh, value, after certain value there will be a non-abelian group of that order? No, because you have primes, right? And for primes, you precisely get a single non-isomorphic group that is the cyclic group of that order, right? And primes, so for any integer n, you can get a prime p such that n is greater than p and p is sorry n is less than p and p is prime. For odd, that won't be the case. I don't know whether this is an open problem or it is known that the primes cannot be bounded. But as far as you can do the calculations, you can always get primes which are of odd order, and the groups of that order is uh, always abelian, in fact cyclic. Okay. A similar statement is not true when we are considering groups of odd order. Okay.
Okay, so
Uh, can you produce one more example? So you know that the smallest group is of smallest non-abelian group is of order 6, right? That is S3. So this 546 is also divisible by S3, divisible by 6, right?
yes,
So can you construct a group of order 546 using a S3? Just take the direct product of S3 with any group of order 546 divided by H. Also also the group is where order of H is 91 is a non-abelian group of order 546. Because order of this group will be order of S3 times order of H, right? Which is 546. And since one of the component is non-abelian, the group will be non-abelian. This is direct product. I know that you guys are not aware, may not be aware with this, but for the moment, you can just take this example. Later on, if we will discuss direct products, then we can see this, or we can independently read what is direct product of groups. That is not difficult. Okay.
Okay, sir.
So you have many examples. This 91, you can just simply take Z91 also. So H can be abelian, non-abelian, anything, but one factor is non-abelian, so the group will be non-abelian. Okay. So uh, now, second one, if H is a normal subgroup of order 42, then the quotient group G by H is cyclic.
This is true.
This is
So,
true. Why?
order of G mod H is 13 and
Hmm,
13 is a prime. So
good. So this implies the order of uh, G, not this. This implies order of G by H is 546 by 42, which is uh, 13, right? Right. And which implies G by H is Z13, and that will give you G by H is cyclic. So this is correct. What about the third one? If H is a normal subgroup of order 7, then the quotient group contains an element of order 7.
this statement is not true.
Then you have to give me a counterexample.
Suppose G is some group of uh, o- order 14 and then
Or,
order of G mod H would be 2, so it can't contain an element of order 7.
no, H is a normal subgroup of order 7.
Okay, so um, I consider uh, Z mod uh, Z mod 14Z and Z mod 7Z. So, oh,
So
I'm sorry, I just need to think about this.
G is a group of order 546. Inside G, there exists a normal subgroup of order 7. Then it says the quotient group G by S contains an element of order 7. So you need to give me G of order 546. You need to give me a normal subgroup inside it of order 7. And then we need to show that the quotient contains does not contains an element of order 7. What is 546 divided by 7? Hmm, 78, right?
Yes, sir.
The order of quotient of group will be of order 78. Can it have an order group element of order 7? Just stick to the basics. So order of G is 546, right? This is given if order of H is 7, then what will be the order of G by H? 546 by 7, right? Which is 78. Can a group of order 78 contain order 7 element?
No, sir.
No, right? Since 7 does not divide 78, therefore G by H cannot have an element of order 7. What about the fourth part? Fourth part says if H is a normal subgroup of order 7, then H contains an element of order 7.
This is true.
This is true by Cauchy's theorem, right?
Yes, sir.
Okay, good. That completes this question. We can move to the next part. Let's take it this much here. So, okay. Let G be a cyclic group of order 330. Which of the following are possible orders of the quotient groups?
Mm. 6 and 55.
6 and
55.
55. Why?
Well, only 6 and 55 divide 330. 12 and 45 don't divide it. So,
Okay. So we know that all subgroups of a cyclic group are normal, right? You take any group, any subgroup, it will be normal and the quotient group will be there. Also, the subgroups of a cyclic group are in, or maybe I can say it in a better language. Also, there exists exactly one subgroup for each divisor of the order of a cyclic group, right? There exists exactly one subgroup of for each divisor of the order of a cyclic group. Whatever cyclic group you have, take its order and corresponding to each divisor, you will get exactly one subgroup. And these are the only subgroups. Divisor, the order of cyclic group. Okay. Now, from where can we conclude that there will be a quotient group for each divisor of a cyclic group? Let For the moment, let me just uh, rewrite this thing. Maybe uh, just I want to be more uh, clear. So R normal, that is fine. So let G be a cyclic group, right? I will just rewrite this. Finite cyclic group uh, of order n, right? What can you say about uh, the subgroups? Then for each divisor of n, there exists a unique subgroup. This stands for there exists a unique subgroup of order and in is right. But what can we say about the quotient uh, groups? Claim is for each divisor of n, there exists a subgroup, there exists a quotient group of oh, there exists a quotient group of G. Can you tell me how we can prove this?
Um, well,
Just try to say something.
um, so for each divisor of n, if there's
Uh,
some normal subgroup,
right?
then I can construct a quotient group, right? I thought
How?
this alone was sufficient, but uh,
Let m divides n, right? We need to find a quotient group of order m.
so there exists some d such that md equals n. So I
Yes,
take a normal subgroup of order d.
no,
That's
it's even
sufficient, right?
easier, right? It's very straight. So let m divides n, right? Then can we say that n by m also divides n because n by m times m is again n, right? You got this point. So I'm just saying then this will implies that m by n also divides n. Since m divides n, oh, something wrong. N by m I should write. n, this is an integer, right? Because m is dividing n. Now this is dividing this. This also divides n because this times m is just n. For example, if 2 is dividing 6, then 6 by 2 is, that is 3, it also divides 6, right? And that is 2 times. Clear?
Yes, sir.
Okay. So now we can use the above criteria that there exists H normal in G uh, with order of H to be just n by m. And this implies order of G by H is just n by m, which is m. So for each divisor of n, there exists a quotient group of G, and that's it. So not just there exists a subgroup, the subgroup is normal, and also there exists a quotient group. Cyclic groups are very nice in such way. So 6 divides uh, 330, I guess. So this will be correct. 12, and also uh, these are the only uh, vector groups, the quotient groups of G. So can you check this? Why? See, the subgroups are fixed, right? They are precisely those uh, which corresponds to a divisor of order of G, right? And exactly one such. And for each uh, normal subgroup, you will get a unique quotient group, right? And you are actually getting all quotient groups uh, corresponding to a divisor. So the number of subgroups is same as the number of normal subgroups, because each subgroup is normal, and that is same as the number of quotient subgroups, right? And since the normal subgroups corresponds only to the divisors of order of n and they are unique, we have also shown that the quotient group also corresponds to the divisors of n. Thus, they have to be unique. If they are not unique, then there will be more quotient groups than the normal subgroups of G, right? Which is a contradiction. You understand my point?
Yes. Yes, sir.
So, uh, so the quotient group can be less because for two normal subgroups N1 and N2, it might happen that G mod N1 is isomorphic to G mod N2, right? So the number of quotient groups is anyway less than equal to uh, number of non-isomorphic quotient groups is anyway less than equal to number of non-isomorphic normal subgroups. But we have shown that they are exactly same and they are satisfying the same similar kind of relation. So since normal subgroups corresponds to the divisors of n and quotient groups also corresponds to divisors of n, and normal subgroups are precisely those. Thus, the quotient groups have to be precisely those which corresponds to the divisors of n, right? So that gives the other side that if something is not dividing the order of the cyclic group, then it cannot have a uh, cannot be the quotient group. This is even true for any group, not just the uh, not just for cyclic group. That the order of quotient group must divide the order of G. That is a basic thing because what is order of G by H. This is just order of G times order of H, which implies order of G is order of G mod H times order of H, right? So order of G by H always divides order of G. So this is like we don't even need uh, group to be cyclic. So if something is not dividing order of G, you cannot have a quotient group of that order. Okay. Cyclic groups are special because there exists a precisely one uh, factor group corresponding to each divisor. Okay. I hope I am clear.
Yes, sir.
Okay. So here I think 12 will not divide. So there will not be any uh, sub quotient group. 45 also will not divide. 55 divides. It will be. So with this assignment 4 is over. If you want, we can discuss some more questions, extra questions, or we can also start assignment 5. But there won't be much questions that we'll be able to do because we just have, I think, uh, 13 to 15 minutes. So what you suggest? Shall I
Either
discuss
way
some
is
similar
fine.
problems or
Okay,
next
sir.
assignment?
Either way is fine, sir.
Okay, so let me just discuss some problems which are not same from the last year assignment. Okay, let's see this part. Hmm. This was problem 1 in last year's assignment. Uh, You can just avoid this 4 marks. Let G be a group of order 648 and H be a normal subgroup of G of order 18. Then one need to choose correct of statements. G by H has order 36. Similarly, you can just divide, and I think since order of G by order of H is what? Is 648 divided by 18 with 3 and 2. This should be true, right?
Yes, sir. This is true.
Okay. The question group contains an element of order 8.
This 8 is not a prime, so I don't think this is necessarily true.
Again, we don't even need 8 to be prime.
Well, 8 doesn't divide 36.
It
Yeah.
doesn't divide. So that will only do the job. But you are right. If instead of 36, we would have 32, then we can get groups of order 32 which don't have an element of order 8. For example, you can just take the direct copies of uh, Z mod 2Z 16 times, right? That is an order group of order 32, but it will not have a element of order 8. All non-identity elements are of order 2. Clear?
Yes, sir.
Either way, it is fine. I'm just mentioning 8 does not divide 36. Okay. Now, number of left facets of H in G is 36. That we have already seen similar question, and this is not true. So this is exactly the same question, only the number has changed. Maybe I try to discuss something which is not of the same nature. All other problems seems to be the same nature. The assignment, last year assignment also, the problems are of the same nature. So maybe we can discuss one or two problems from the next assignment. Or if practice assignment you want, we can discuss some practice assignment problems of week 4. Uh, they will be of different flavor, I guess. But I think we have already discussed that earlier.
Sir, for the practice assignments, I think uh, it was discussed only up to assignment 3.
Okay. Mm, then we can take some good question from uh, this one. Or okay, I'm just taking one random question from a practice assignment. I think this will be the last problem of this session. Yeah. So let G be an arbitrary group of order 480. H be a subgroup of uh, G. Choose all the correct statements. The order of H divides 480. This should be correct, right? By Lagrange's theorem. If H is a normal subgroup of order 96, then the quotient group G by H is cyclic. Is it correct? Correct, right? The quotient group is of order uh, just 480 divided by 96. This is of order 5. And all subgroups of order 5 are just isomorphic to Z5, which is cyclic. If H is a normal subgroup of order 5, then the quotient group contains an element of order 9. This one you should tell me. Uh, order of G by H is 480 by 5, that is 96. They have given again very easy uh, conclusion. 9 does not divide 96. The same thing is following here also. So nothing new. This implies there does not exist an element of order. Now, fourth one is correct because two is a prime number. Since 2 is a prime number, dividing 96, therefore, uh, there exists an element of order 2 in G by H. Now, fifth one, uh, you have a normal subgroup of order 32, then order of G by H is 480 by 32, will be 15, I guess, right?
Yes, sir.
And again, since 2 does not divide 15, there exists no element of let us see something more. So in part 3, can we ask, does there exist an element instead of 3, I should write Roman, right? Part 3, does there exist an element of order 4? 4 is dividing 96, right? 4 is clearly dividing 96. Can we say there exists an element of order 4 in the factor group G modulo H? Can we get an group G of order 480, a normal subgroup of order 5 inside it, such that the quotient group does not contain an element of order 4? So we need to take examples like that. Okay, so the best way to consider such examples is through direct products, because each component of the direct product is normal. So we need not to check the normality. You just take some group of order 5, some group of order 5, and order 5 is, there is only one option, so you need to take Z5 only. Now you take direct product with something which do not have an element of order 4 in it. This part won't have an element 4, this part won't have an element 4, and element of the direct product has order. For example, the element of A comma B, that it has the order which is LCM of the order of A in the first component and the order B in the second component. So if there is no element of order 4 here, there will be no, and there is no element of order 4 in the second part, then the group cannot have an element of order 4. But you need to check just if there exists a group of order 96, which is which is not containing the order 4 element. That's basically now the task. Again, you can uh, take the group Z2 raised to 32. Oh no, 32. So the prime factorization thing you can use. So 96 is keep Z3 one side, then you are left with 32, right? You take Z2 16 times. This is a group of order 5 into 3 into 2 into 16. You're taking 16 times 2, right? This will be 480, right? Now you simply take H to be this Z5. Then, since You are taking it in direct product. G by H has no element, or not Z5. You take Z5 cross identity cross because H is, you have to make sure that H is inside G. So identity 16 times. So this is inside, this subgroup is inside, uh, not 1, 0, I should write. So this is the set, mm, this is the group which has other all other coordinates to be 0, and in the first coordinate you are taking element from Z5. So this will be sitting inside G, and uh, then G by H will be just isomorphic to whatever is left, Z3 cross Z2 16, and G by H has no element of order 4, right? Because this has no element of order 4. Now the task is, I am leaving you with this exercise. Can you give me a non-abelian group of order 480, non-abelian group G of order 480 with H normal in G such that G by H has no element such that order of H is 5, and G by H has no element of order 4. So I have constructed an abelian group. Now can you give me a non-abelian group? You understand the question?
Yes, sir.
G of order 480 with H normal in G such that order of G is 5 and G by H has no element of order 4. So you have some idea. So here we have taken everything to be uh, Z3 times Z2 raised to 16. Try to somehow fit S3 here. That's a good hint. You can go with the Z5, and here try to somehow fit S3. Then it will become non-abelian, and then uh, you need to construct a group which is non-abelian and which satisfies this property. Okay?
Okay, sir. Mm.
If there, if there are any doubts, then you can ask. Otherwise, we can stop the session here.
No doubts, sir.
Okay, thank you. So, one announcement. Uh, there will be an extra session, I think, on the coming Saturday, probably, of 2 hours at the same time, 6 to 8. So most probably you will get the confirmation by Friday. So you can attend that session, and we will try to complete the next assignment, that is assignment 5 in that session. Okay.
Yes, sir.
Okay. So I'm uh,
Thank you, sir.
okay. So I'm just ending the meeting here.